All right, we're going to talk about the second derivative test for absolute extrema, absolute maxes and mins. It's fairly straightforward. If x equals c is a critical point and my function is continuous on its domain, and my second derivative is always negative, always, 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 for all x in the domain, right? So if f double prime is always negative, then what must be true? My original function is always concave down. And concave down looks like a max. If this guy is always concave down, f of c here is not just a local max, but in fact the absolute max. Now, on the other hand, if instead of the second derivative always being negative, if the second derivative is always positive, then we know my original function is always concave up. Right? Then what must be the case? F is always concave up, and concave up looks like a minimum. And the key difference here between my second derivative test in general, the key difference is here saying for all x values. If my function is always, always, always concave up, the place where I've got my critical point is not just a local, but in fact an absolute minimum. Now let's also go ahead and talk about example 2 using this test. All right, so my objective function from example 2 again, that was a is equal to 2400 w minus 2w squared. And we were highlighting that in pink. Okay, and previously we went ahead and found the first derivative. And we set it equal, there's no places where it's undefined, so we don't get any critical points that way. We set it equal to 0, and we found out that w equals 600 was our only critical point. We can't even write that. Okay. Now, if I take the second derivative, the derivative of a constant is 0 minus the derivative of minus 4w with respect to w is just minus 4. We get that our second derivative is always negative 4. The second derivative is always negative, therefore what? Therefore a, and again you probably know this already because a is a quadratic, but We're just illustrating a point with a simpler example. Therefore, A is always concave down. I even think it's helpful to draw a little picture of that and go, oh yeah, concave down results in a max. Therefore, A of that critical point, which we calculated in example 2, isn't just a local max, it's the absolute max area in feet squared. And I think with this particular problem, aside from noticing that it's, aside from not doing calculus, right? Aside from noticing it's a parabola and finding the vertex, I think with this particular problem, although it was doable to identify the domain as being closed and bounded, I think that using the second derivative test for absolute extrema is by far the easiest. You have A, you get A prime, you get A double prime, and you go, oh my goodness, A double prime is always negative. This function is always concave down. Therefore, it achieves an absolute max. And where does that occur? It occurs at the critical point. Okay? So what we have done now is we have illustrated the 3 different approaches to finding absolute extrema in context.